Before we go deeper, let's understand what a tree is in discrete mathematics. A tree is a connected graph that contains no cycles. This means all vertices are connected and there is no path that returns to the same node. A rooted tree is a tree where one vertex is designated as the root. All other vertices are connected through parent-child relationships that originate from this root. One important property of a rooted tree is that a tree with n vertices always has n minus 1 edges. Next, we have a binary tree. A binary tree is a special type of rooted tree where each parent node can have at most 2 children, commonly referred to as the left child and right child. Binary trees are widely used because they provide an efficient way to organize and process data in computer science. Let's go to the next slide. Okay, trees are not only theoretical concepts in mathematics, but they also have many practical applications in real life. First, trees are used in computer file system to organize folders and subfolders, making data storage and retrieval more efficient. Second, website navigation structures often use tree-like hierarchies. Starting from the home page, users can move through different levels of pages in a logical manner. Third, organizational charts in companies use tree structures to represent reporting relationships between managers and employees. Finally, tree structures play an important role in artificial intelligence and machine learning. Decision trees help AI systems evaluate different options and make decisions based on branching paths. This example shows why tree structures are fundamental in both mathematics and modern computing. That's all from me. Thank you.
Moving on to slide 4, let's look at one of the more practical application of tree, the binary search tree, or to simplify the term is BST. When we deal with massive datasets, searching for items linearly is highly inefficient. A binary search tree or BST solves this by keeping data systematically ordered. The rule is elegant and simple. For every parent node, the left child always holds a smaller value, and the right child always holds a larger value. As you can see, note here, to search for an item, we start at the root. If our target is smaller, we start left. If it's larger, we start right. This simple choice cuts our search space in half at every single step, shifting our operation time from a slow linear search straight into highly efficient logarithm time. It is the foundation of fast data retrieval in modern databases and file indexing systems. Now, please turn your attention to slide 5, where we discuss tree traversal. Because trees are non-linear structures, we need a predictable, programmatic way to visit every single node exactly once to process its data. Depending on the order in which we visit the root and its subtrees, we have 3 fundamental traversal algorithms: pre-order, in-order, and lastly, post-order. First, we have pre-order traversal. The strategy here is to visit the root first, then move through the left subtree, and finally the right subtree, as you can see on the slide. This top-down path is exactly what developers use when they need to copy an entire tree structure or generate prefix expression for compliance. Second is in-order traversal. Here we visit the left subtree first, handle the root, and then finish with the right subtree. The remarkable thing about in-order traversal is that if you run it on the BST, we just discussed on the previous slide, it will extract and print your data in perfect sort ascending order. And finally, we have post order traversal. This algorithm prioritizes the subtree completely, visiting left, then right, before finally processing the root node at the very end. This bottom-up approach is incredibly safe for memory management when deleting trees, and is essential for machine evaluating profits arithmetic expression via stacks.
Next, I'm going to explain about expression trees. One example of the expression I can give to you is x plus y to the power of 2 plus x minus 4 divided by 3. Every operator becomes a node, and every variable or number becomes a leaf. The tree structure reveals the order of operations visually and logically. Next, I'm going to explain about the infix, prefix, and postfix. These notations are used in programming and compilers. Each represents the same expression differently, affecting how computer parse and evaluate mathematical operations. So, for the first example, it is about the infix notation. The simplest example I can give is the x plus y. The operators will sit between the operands and is natural for humans to read, but it requires parentheses and precedence rules for compilers to parse correctly, in which, as we have learned before, it is about we have to solve the operations inside the parentheses first before we can proceed to the other operations. And then we have prefix notation, which is the plus xy. The operator comes before operands, also called Polish notation. No parentheses needed, and compilers will evaluate left to right with ease. So in the trees, the system will read from the upper and then go down to the left, right, and then so on. Last but not least, here we have a postfix notation, which is the xy plus. The operator follows operands, which also called reverse Polish notation, RPN, and it is used in a stack-based evaluation efficient for machines and calculators. Usually, the system will read the trees from the bottom to the top. Next, we have a MATLAB tree visualizer. These notations are used in programming and compilers. Each represents the same expression differently and affecting how computers parse and evaluate mathematical operations. So the purpose and the overview here is the MATLAB tree visualizer is designed to graphically represent and analyze tree structures in discrete mathematics. It provides an intuitive interface for constructing rooted trees, binary trees, FVL trees, and spanning trees, which enables students and researchers to explore structural properties visually. It also supports multiple trees binaries such as BST, FVL, and B-tree. Real-time rendering of nodes V and edges E subset V times V. You also have the depth, height, and degree annotation on each node. The key features here are interactive visualization, which dynamically will and modify tree structures with live graphical output. Next, multi-tree support, which seamlessly switch between tree types, in which here we have T equal to V, E for comparative analysis. Next, we also have academic integration, which will align with discrete mathematics curricula for enhanced learning. Research ready, in which we export visualization for reports, papers, and presentations. Last but not least is annotation tools, which label nodes, highlight subtrees, and mark tree properties automatically. Next is the MATLAB implementation. As you can see here, this slide demonstrates the MATLAB implementation of the tree visualization system. The program takes hierarchical and represents its tree structure, where each node is connected to its parent and child nodes through directed edges. In the figure, node 1 acts as the root node. It branches into nodes 2 and 3, which further expand into leaf node 4, 5, and 6. The arrows indicates the direction of traversal from parent nodes to child nodes. The implementation uses MATLAB's graph and diagraph functionalities to create and visualize the trees. Coordinates are assigned to each node to ensure a clear hierarchical layout. Different colors are used to highlight important nodes. For example, the root node is marked in red to distinguish it from the other nodes. This visualization helps users easily understand the hierarchical relationships within the tree and verify the correctness of tree construction and traversal algorithms. The generated output confirms that the system successfully creates and displays the tree structure according to the provided input data.
My name is Muhammad Aiman, and I will discuss the result and analysis of our tree structure implementation. For the binary tree, the output shows a balanced structure with a depth of 4 levels. The parent-child relationship are clearly visible, and both the left and right subtree maintain a nearly equal height. This demonstrates an efficient tree organization that supports faster searching and traversal operation. For the AVL tree, the result confirmed that self-balancing rotation was successfully applied whenever needed. This ensures that the tree remains balanced after insertion, preventing performance degradation. In addition, the spanning tree visualization shows a minimal set of edges connecting all of 12 vertices without forming any cycles. This verifies that the spanning tree correctly achieves full connectivity while minimizing redundancy. To conclude, tree structures are an essential concept in discrete mathematics and computer science. Throughout this project, we explored several important types of trees, including binary trees, AVL trees, expression trees, and spanning trees. Each structure serves a unique purpose, from organizing and searching data efficiently to representing mathematical expression and connecting networks. These applications can be found in databases, file systems, compilers, and many other real-world computing systems. Using MATLAB, we were able to visualize these structures and better understanding how they operate. The visual representation made it easier to analyze their properties and relationship. In summary, this project has helped us gain a deeper understanding of tree structures and their practical importance in solving computational problems. That's all from us. Thank you.